Okay, so we are going to have a discussion session about probability, and I'm glad that we have the longer discussion session for this particular topic. Let me open with a short, just a personal reflection. So we opened this workshop with Valia talked, in which she gave the argument that many worlds has something of a principal explanation, and I was puzzled that I heard it, because I know the story as has been told, for example, by Jeffrey Boob. So the interpretations are, in Einstein's terms, the constructive approaches, and then information theoretical approaches are truly principal approaches, and the teacher, Daniel Rohrlich, has his own principal approaches, but I never thought of the many worlds interpretation as different, for example, from Bohmian mechanics in this respect. And today, the discussion about probability, it seemed to me that maybe probability is the issue where the different types of explanations actually come up. So we have time to dedicate for the questions of where this probability coming from. So we'll have Dustin starting, and then Lou and Per.
So, as I formulated the open discussion, does it make sense to ask what is the probability of an outcome of a measurement before the measurement has been carried out? This is really the question which I want to understand, and the meaning is, as a philosopher, I want to answer a philosopher. Let's say we cannot ask this question. Is it still okay? Because I find this solution with self-location, and it's not clear. Some people accept, some people not accept. I know that Simon had this idea that we can ask about uncertainty in many words even before, but just in a conversation now he says that he doesn't want to push this idea, at least strongly, and I want to understand this issue. I hope there will be time for this. We have like maybe 40 minutes now. But I want to start with a question to Dustin, which the question QA was stopped, and I think it's important because I didn't get the story. I don't think there is any, you cannot have analogy between classical probability and quantum probability, because as you said, here you have this initial state, and then you have this final result. And this particular details of initial state will tell you the final result. This is not the story in quantum mechanics. And this is why I think it's so different. So if you consider this like quantum, and if you consider every one of them really put 99% to the right, and 1% to the left, it's happened quantum mechanically. Then your distribution in the end will be something like this. But the number of words remained exactly the same. The numbering, you said that in most of words, statistic is correct. The quantum statistic will be like this, but if you count the number of words, it will be the same like here. So how you resolve this paradox? This is kind of the main paradox when we repeat quantum experiment. If we do it with a beam splitter 50-50, we get standard result and everybody agree. When we repeat quantum experiment with beam splitter 9-1, the number of words and the type of words didn't change, but the statistic changed. So in this way, you cannot use counting of words to get statistic. I didn't get it from your talk, how you do this.
Does this still work? Yeah. Okay, so yeah, maybe I should address at least two things about your question, but starting with the point you made at the end. I think you basically made the argument that naive branch counting doesn't work, right? If you just count branches, then it's not true that in the great majority of branches you get Born statistics. And that's, of course, undisputed. That's, of course, right. So the question is, why you shouldn't determine typicality. What do you mean by the great majority of branches by branch counting, right? And one answer is that branch counting is a complete non-starter because the number of branches, the number of worlds, is not even well defined. And like decoherent-based theories, and like David Wallace's understanding, there's no definite number of branches, right? You can take a, what?
Here, it's well defined.
Here?
Well, why here it's not well defined? You have this story and you have detector. You consider this example quantum mechanically. You have exact. Here it's everything defined. So, but this cannot be. So, what will happen here?
What do you? I'm not sure if I understood what you mean by consider this quantum mechanically.
This.
So here you have infinitely many possible initial conditions, right? I mean, on a coarse-grained level.
In a classical case,
yeah,
the initial condition really will change depending on this. In a quantum case, this is what's special about it. It doesn't matter if you move it a little, the probability is still the same.
If you move if you move what a little?
When you have a beam, usually I have a beam splitter. And classically I can say, no, there are some holes. I send a bullet. If it's through the hole, it goes through. If it's not exactly through the hole, then it reflected. And so we go to the quantum particles, shoot them. Sometimes they go through, sometimes they reflect it. So the original idea, maybe there are some structure, and depending of my shooting, it will be different. But I think equations and all experiments tell us that we don't have to worry exactly how we shoot our photon. The probability is the same of this beam splitter all the way. So the same here. With classical device, it's very important where it's come. But if it's quantum thing, you shift it a little initial condition, you will not, the equation will not change. So it doesn't have only one story.
Yeah, so what matters or doesn't matter, at least counterfactually, is always a question of the dynamics, right? So of course, in quantum mechanics, you have different dynamics than in classical mechanics. But maybe I should also, or maybe...
The idea is the quantum counterpart, I have a beam splitter, I have a photon, and then another beam splitter, many beam splitter. What, quantum information people, they can say that quantum, that they have permanent, they can solve permanent faster by quantum interference.
But maybe I should clarify the other aspect. There's, of course, an important difference between the typicality reasoning in this case and the typicality reason in the Averatian case, that here is a typicality reason over possible initial conditions, right? So the reasoning has a decidedly modal character, right? There are all these possible initial conditions, and you can, of course, you also ground counterfactual if the initial conditions were different.
So this is why analogy doesn't work, because in quantum mechanics, all initial it's not, the results are not sensitive to initial conditions.
Right, that was not the point of the Everett
classical case are not sensitive.
No, that was not the point of the Everett argument. So the Everett argument...
This is about your analogy. You said the Boltzmann and Everett had something similar. But for Boltzmann, I think it's crucial that it's sensitive to initial condition. And in Everett, it's not sensitive to initial condition.
No, but there the question is for one multiverse, right, with a given universal wave function, right? What is the statistical distribution in the vast majority of branches, right? So there the question is not what happens for a typical initial condition of the universal wave function. That would be another level that would be very interesting to analyze and think about, but that's not the issue in the Averatian case. So in the Averatian case, we have one multiverse with one universal wave function, but we have an ensemble of world branches, like again, maybe ensemble is not the right word. We have a huge or possibly indefinite number of world branches in this universe, and then we ask what statistics obtain in the vast majority of branches. So there, the typicality statement is not with respect to an ensemble of possible worlds, but to an ensemble of real, equally actual world in an Averatian multiverse. And still we have a typicality result right, that in the vast majority of branches, the Born statistics hold. But what does it mean? By what measure vast majority of branches? Not by simple branch counting, but by the measure that is given by the amplitude squared of, the coefficients of the world branches. And this measure of typicality is justified by the assumptions that Everett made.
Okay.
So that gives you a time-independent way of counting and gives you a consistent way of counting, even if the branching process is vague and not sharp.
Difference than counting or weights. If you count, there is no weights. And of course, somebody said that if everyone has the same weight, then it's obvious counting will work. So, but when the weights are different, and the question is, do you get the equal weight for all branches?
Yeah.
And usually you don't. So then counting doesn't work.
No, that's a good point. Now you argued like a good philosopher pointing out my imprecise use of language. So a way of quantifying what we mean by the great majority of world branches, right? And it's not by naive counting, which probably doesn't even make sense, but still by the assumptions that Everett gives. And then one can debate whether these assumptions are justified, but they seem very reasonable to me. And that sort of justifies Everett's notion of how do we quantify what we mean by nearly all or the great majority of branches within the multiverse, right? And then in a great majority, we find that Born statistics hold along the histories.
Okay, so I suggest we take two short questions, if possible, and then we'll move to the next discussion. So Simon, you're first. Anyone?
Yeah, just to Dustin, I mean, you may disagree with my talk. Did you come to my talk?
Yes, yes.
So
and
I gave a rather elaborate, I thought, and clear analysis of how you can count branches.
Yes.
So you may disagree with it, but I'd rather not be completely ignored, that's all.
What? No, sorry, I didn't. Certainly, I didn't mean any disrespect. I was just responding to Lev's suggestion, which was based on naive branch counting. Like when he says independent of the coefficients, you always have the same number of branches. I was just. Okay. Sorry. No. Sorry. I should have acknowledged it. And I actually think, and I don't know if you take that as a slide or as a compliment, that your talk was, I think, very close to Everett's argument. And I disagree only in that far that it's not frequencies all the way down, but at the bottom is a notion of almost all, a notion of what is the great majority of branches. Right. Yeah. With same amplitude. No, but yes, of course. But then also, many of your interesting statement was also for most, right? Like in most branches of most of my future, right? Right, and that's like translates well into the typicality, man. Yeah, but no, so I apologize if I didn't. Yes. Yes, right, and I'm very sympathetic. I'm sympathetic to that. That would just say that Everett's argument, how I understand it, at least in the typicality language, right, asks people to accept less, right, not agree that here's a way to say that there are 5 branches here and 7 branches there. Just this is a reasonable criterion for what we ultimately mean by most branches or a very large set of branches. So it's a more modest, in a sense, what you need to grant. Yes. Yeah, I know what you mean. Yeah.
Okay, Tomer?
Okay, thanks.
Try to keep it short with 2 more.
Sure, very short, yeah. I think that you considered the empirical distribution and the theoretical distribution as separate entities. But if you consider, for example, the game that you gave with the balls, then when you consider the empirical distribution and you do an infinite number of trials, you will find that the theoretical distribution, which is the normal distribution if they are independent, following the classical limit theorem. So you don't have to assume anything, right? You can get the theoretical distribution without assuming anything, just you do infinite number of experiments. So I think that
typically you get it. Yeah.
This is the difference that it is close to what Lev said about the difference between classical mechanics and quantum mechanics, because in the classical sense, you have different initial conditions, then maybe you will have different distributions, but in quantum mechanics, you have different initial conditions, but it doesn't matter about the post-selected state, the final state of the system. So I think
it's the same if you consider a limit
there is a mixture of different things that you said, like theoretical distribution. What is the theoretical? Because there are two types of theoretical distributions. The one that you can get from infinite trials and the other that you do goodness of fit, like is postulating the Born rule, for example.
What do you mean that one can get from infinitely many trials? You do infinitely many experiments.
Here, no, yeah, on theory, how you get the classical limit theorem. This is what you do.
What?
Classical limit theorem, you know it?
You mean the strong law of large number, or what?
No, that if you have independent random variables that are standardized, you get normal distribution, theoretical probability distribution.
Yeah.
Yeah, I think it will be a big discussion.
You mean the central limit theorem? Or?
Yeah, okay. Central limit.
Now,
yeah, so what?
Yeah, I'm sorry to cut it with 2 more discussions.
I didn't understand. Yeah, I didn't
No,
really
we'll
understand.
talk about it later.
I didn't really understand what the.
We'll talk about it.
I didn't really understand what the objection. I didn't really understand what the objection was. But yeah, of course, if you take infinite limits, then typically that means with measure 1, you get the theoretical distribution. Yeah, but of course, but usually physically relevant are usually large but finite samples, and then you get just close to the theoretical distribution.
Thank you, Dustin. It was very helpful for clarifying. So we now have the next discussant, Lou, and then Paul.
Okay, thank you. Just until Lou is coming down and settle, may I just have my kind of sentiment. Classical probability theory has nothing to do with classical physics. And I'm not interested. And physics is not described by infinities. You don't go to infinities in describing the world. This is what I believe. So anyway, result of probability theories will have randomness. I don't believe there is randomness in nature. So whatever classical probability theory says, this is not what classical physics says. So we have to choose the word. So classical physics, and here it was classical physics example, not necessarily classical probability theory.
But there are probably infinitely many branches of the
The universe has finite number of quantum states, so there's no infinities. No, and the number of branches is much, much, much less. Maybe many. There was discussion here, and I think David says that we shouldn't worry about that. It's very large. It's very large, but it's not infinite. Yes.
If I measure position, then the theory is that the position is described by a real number, and there are lots of these.
Yeah, so it's Bekenstein bound, but also we had this discussion. Nicolas Gisin presented this mathematical, but this is mathematical. Real number, it's a mathematical story, not physical story. When I measure position, I don't have infinite number. Well, my measuring device don't have infinite number of points to say, oh, it's this, and this. It has only finite number of points.
But that is probably a problem with the measuring equipment and the abilities of measuring equipment. You can't say that you can't commit to saying that this is a limit of the universe itself.
There is a physicist said that given particular volume or whatever energy, whatever, we have a maximal number of orthogonal states and different outcomes clearly orthogonal. So of course there is a limit. If energy is infinite, we are in a black hole. So there are limits, and universe had final energy, final mass. So there is we don't need infinities. But we have to. There are other people.
Yeah, I just want to say that I told Lev before this discussion, I said he should manage it. He said, no, someone should stop me. I'm enough. Okay, please do.
Okay, I will make two responses of the topic I have just presented. Well, first response is to David Wallace, who claims in his book, The Emergent Multiverse, that, well, the debates of the overlapping worlds, overlapping branches, and divergent branches is not philosophical significant. That is to say, it is not important. There are not much substantial differences between the overlapping view and divergent view. Well, I just read some paragraph of his argument just a bit time, that insofar as possible worlds are mathematical abstracta, this is a meaningless, or at any rate, a pretty shallow question, akin to asking whether to qualitatively describe the mathematical objects which are partially isomorphic are identical in their isomorphic parts or merely indistinguishable. And I will not read all of his paragraph, and if you want to say it, it's just in his 7th chapter, well, from page 286 to 287. And here, I think Wallace's rejection that there is a substantial differences between overlapping view and divergent view is just it just accords with what I have just said in my presentation in the very beginning, that, well, from an ontological view of how do we understand the ontology of a branch, how do we understand the ontology of a world in errant quantum mechanics, well, they are just the patterns of our understandings of the whole universe. So actually, there make no differences if we make no substantial differences if we accept the overlapping view, or if we accept the divergent view. So actually, they are not. So actually, I agree with David Wallace's idea, but more importantly here, well, what makes the uncertainty possible is that there should be, well, how many minds or how many persons, if we accept three-dimensionalism, or how many person stages are there before the branching. What's important is not that, well, whether the walls, the branching are overlapping or divergent. What's important is that if there is only one person stage before the branching, then there cannot be uncertainty. Well, but if there are more than one person stages before the branching, there could be some kind of uncertainty. And I think this might be the possible motivation for us to accept the overlapping view. And Sanders? Or could I just carry on? I just want to say something else.
A minute or two to close it up, and then we'll have one question.
Okay. And the second response is to Paul Tapton, who just asked me whether my rejection, whether my critics to the Sanders and Wallace is the same as his rejection. Well, actually, I think it is not. Paul Tapton's rejection is just that we cannot use the pronoun I to refer to one single, to refer to either Alice up or Alice down. We can only use this term to refer both of them. But this is an issue of philosophy of language. Well, let me give you an example. Suppose that here, Levi Weidman he has a physical body. But let us suppose that actually he's occupied by two different minds. But these two different minds are just, well, qualitatively identical, but they're actually two different minds. And if I point to Levi Wiedemann, I cannot refer to any one single mind of Levi Wiedemann. I can only successfully refer to both. This is an issue of philosophy of language. But if there are two different minds which all supervene on Levi Wiedemann's body, then it makes sense to say it is this mind who is uncertain, and it is the other mind who is uncertain. And there are some further facts to distinguish these two different situations. So maybe we can successfully refer to the person stage, or maybe we cannot. But whether we can refer to them is one thing, but whether there are some facts to ground that claim is another thing. So this is my response. So I think actually, well, my response to the Saunders and Wallace is different to Paul Tapton's view.
That's right. And make it a dialogue, right? So let's just take Simon's comment and short response, and then.
Great, thank you. I just wanted to say, you made the claim that divergence and overlap is irrelevant. All that matters is, are there more than one person stage prior to the measurement? But divergence just is the fact that there are multiple person stages, qualitatively identical but numerically distinct prior to the measurement. That just is the divergence view.
So
I don't think you ought to say divergence versus overlap is irrelevant. Precisely the distinction you're trying to draw.
Well, I don't think there's any contradiction between you and me. It's just said that from an ontological view, if we only pose the view of overlapping and divergent view, just on how do we understand the ontology of a branch of a word, that there might not be any differences because they are just a pattern of how do we understand them. But if divergent view means that there are different present stages, there are differences between divergent view and overlapping views. So what is important here is whether there are different present stages. So I think there are no
Indeed,
difference
but that's
between.
just what divergence guarantees. Qualitatively identical but numerically distinct person stages prior to branching. That's just what divergence is.
But whether there are many present stages or not does not necessarily rely on the ontology of the branches of the word. Maybe we can have a different ontology, or maybe we do not need to have a different ontology. But I just want to say what is important here is just whether there are, how many present stages are there. So this is what's important. And finally, the conclusion I want to make is just that, well, I think if we want to ground the uncertainty in many words interpretation, maybe this will lead us to some kind of non-physicalism. But I don't think this is a refuse of this is bad. Actually, I am happy to accept some kind of non-physicalism to understand the aberrant quantum mechanics. But the point I just want to make is that last century there are indeed some kinds of understandings of aberrant quantum mechanics following a route of non-physicalism. Actually, in the last century, there are some who adopt the view of many minds, like Lockwood, David Albert, or Barry Lovier, or Download. And actually, I think these views, it seems that are abandoned, or people just no longer care about them in 21st century. So the point finally I want to make is that maybe we should treat this kind of many minds interpretation of quantum mechanics more seriously than its current status. And this is the final remark, sir.
Thank you very much. Yeah.
Okay, I will try to be short this time. So I just want to put up a few points that I value. And something I got from a paper from Papineau a while ago is that the probability in Everett's multi-world should give us how to make decisions before splitting has occurred. So that's one requirement. That's how we use, it comes from how we use probability. So we should be able to use probability. So you use it for decisions and use it for statistical analysis afterwards. And that what the Bond rule states is an objective feature about the world. So from that point of view, the probabilities have to be objective. And then by calculating, I think this comes into what was mentioned here previously in a comment. By calculating what happens after an infinite number of events. So I think, at least theoretically, we can calculate. I mean, we cannot do that in practical, but here we have a theory which actually can give probability. Then we can calculate what happens after an infinite number of events. And we can read off what the frequency is if we have a fundamental understanding of what a wave function is. So that is just some points I wanted to mention that I think that, yeah. Yeah, I want to open that. Is there agreement, disagreement?
Okay, so look, something that Per is saying is, which I know Lev won't agree with, but if it's intelligible to assign objective probabilities to the future branches, then you've got a partial answer to your question. And so then, I mean, I gave an argument why it was intelligible to do that in my paper. Simon has sort of put forward ideas which are sort of at least very suggestive that you can identify branch rate with objective probability. Might be other ways of doing it, but the point I'd like to make, Lev, as well, is that, you know, there's a question of whether you want uncertainty or not. And what I was trying to say is that if you will allow that you can assign probabilities to the future branches, your multiple branches, then what you can do is do exactly the same as what stochastic theorists do, and use the principal principle, and then you assign degrees of belief to the various outcomes equal to what you take the objective probabilities to be. And that is a state of uncertainty. It's a state of uncertainty which doesn't involve alternatives. Well, as the way I put it is that a state of uncertainty is a cognitive state of entertaining partial degrees of belief in multiple futures. And it doesn't matter whether they're alternatives or all coexisting. It's still a state of uncertainty. So you've got your uncertainty, pre-measurement. You don't need to refer to self-location uncertainty.
So you want to say that uncertainties are necessary and they are there. I think that Papineau here helped me to understand that actually you don't really necessarily need uncertainties as long as you can get a decision theory out of it and you know how to do statistics. That's how I took it. But
I think what I'm just saying is whether you want it or not, you've got uncertainty there, because if you're assigning the objective probabilities, just to repeat, if you're assigning the objective probabilities, you can apply principle just the same way as stochastic theorists do it. And so, like it or not, you've got pre-measurement uncertainty.
Probability is consistent with knowledge about the future. Now, Paul's saying uncertainty is consistent with complete knowledge about the future, and that seems to me a perfectly happy way to talk, but it's not going to satisfy the people who want something more.
People who want something more want alternatives, that's the point.
Yeah, so I don't think that uncertainties are really a necessity here, but only that we can make decisions and statistical analysis.
Thank you. I mean, just to comment on what Paul just said, I think, Paul, you would grant that there's no lack of knowledge. So, Per, just on what you're suggesting here, this notion of infinite number of events and so forth, you're familiar with Hartl's work on this and various other people who have looked at, well, what happens with infinite repetitions. You get you don't get a countable Hilbert space anymore. There's all sorts of technical problems. But essentially, you get states, the states with anomalous statistics, their norm is driven down to 0.
Yeah,
Presumably that will give you what you want, does it? I don't know.
Well, let's see. I have it. Yeah, you have something here to talk about. So this is sort of the mathematics, right? And then we can take the limit. The number of cases go to infinity, and that graph there becomes a delta function. Yeah, well, you have some mathematics difficulties, perhaps, but I think they actually sorted out in the literature, as far as I'm concerned. I think it was already sorted out, actually, 1968 by
Hartle, that's what I just said.
By Hartle.
That's what I just said, Hartle.
Yeah, okay. Okay, I didn't hear you. No, right. So I think that was sorted out. So I don't see that there is a problem. Okay.
Yes. Can you go back to your first line?
Yeah, sure. I'll try.
Yeah.
I'm sort of...
So I would like just to comment on your statement. This is good enough. Maybe short comment. I think this was expressed. I believe that all this frequency and whatever, many words or not many words, I think this was expressed before. There is no difference between the many words and any other thing. And also many words cannot be, there is this fact that in many words everything happened, but in collapsing everything can happen. And there is no any observation of difference between this, so there is no, I don't think that in this part is make any difference between many words and others, and we don't have to go to infinities, as I said, because we don't have infinities. But I want to go to the beginning. If this is your definition of probability, then in my picture, I have no any uncertainty. I know there will be splitting, and there will be different words. They will have different measures, and I care about them differently. This will make my decisions. I will make my decision according to this carrying into this measure of existence of future words. After this word created, I can make statistics, and I expect, according to find born statistics. So everything is, for me, consistent with ideas that there is no uncertainty, there is only definite splitting, plus self-location uncertainty. My question, if there is other option, I cannot see it. And if somebody want to present it clearly, because what Simon says about numerical, I never was able to understand. Well, what does it mean? It's identical, but somehow it's not identical. I don't understand what it is. I need some physical parameter which tells me what is the difference. And until I see it, I don't understand it.
Yeah, well, that was not a question to me, I think.
This is a direct response to Lev. I need to think about the best way to answer your question. I mean, this was a broader comment about the uncertainty in this context. I mean, here's an analogy. I mean, it would have been reasonable at one point, it probably was normal at one point, to have said in philosophy, in epistemology, that to be uncertain about something was for there to be some proposition whose truth value you didn't know, some third-party fact about the world you didn't know. And then Perry and Lewis and people convinced basically everyone that there was another species of uncertainty whereby you could know all of the relevant propositional data and have some self-locating lack of knowledge that you could, that some, and so the notion of what counted, the analysis of uncertainty changed and allowed for the fact that uncertainty could include uncertainty of where I am, even if I don't know all the facts, if I know all the relevant third-party facts. That was optional. I mean, somebody could have thumped the table and said, no, that's not uncertainty. I want to insist that to be uncertain about something is for there to be some proposition of truth value you don't know. And that could have won the day. And it could have been that we'd agree we won't use this word uncertainty to describe the epistemic situation and the decision theoretic situation of having, of what we actually call self-locating uncertainty. But that choice of language use wouldn't have made the decision theoretic and epistemic problems go away. We'd still need to have done an analysis of what people in that situation should do. And that analysis would have looked isomorphic to the analysis we actually do in terms of self-locating uncertainty and self-locating decision theory. And it would then be a rather shallow semantic matter as to which of those ways of doing things we prefer. I think this is fairly similar. I think it's possible that there's an analysis, if you like the kind of analysis that Simon and I suggested, it's possible you can do an analysis of Everettian uncertainty in terms, as a variant of self-locating uncertainty. But maybe you can't, or maybe you don't want to go there. Then I think you still got the choice. You could say, well, I will broaden my notion of uncertainty, and I'll allow an answer to the question, what am I uncertain about, to be I am uncertain about what I will experience, even if that doesn't reduce to present tense first person uncertainty. Or you could not do that, and you could thump the table and insist on the previous notion. But it wouldn't change the fact that you'd have to do the epistemology and decision theory of agents in this new situation. And again, the analysis is going to look isomorphic either way. It will work or it will not work, depending how you resolve the Everett probability problem. And again, it will become a somewhat shallow issue, I think, whether we decide to genuinely broaden the term uncertainty, or if we want to thump the table and hold on to it and just say, okay, this is a psychological decision theoretic state with certain formal analogies to uncertainty.
We've finished. Let's thank all of our speakers and enjoy this topic.